So, good morning, ladies and gentlemen. Today we are having the program Lightning Protection. All you want to know. As you are aware that this program has been organized as a part of VIDYUT SURAKSHIT Bharat Abhiyan, which is All India Mass Awareness Campaign on Electrical Safety, which we started last year. 1 year we were trying to make a lot of awareness classes. Today we are going to discuss about lightning protection. And this program actually it consists of 4 sessions each Sunday starting from 11 o'clock onwards. Today is the first day. So coming 3 more weeks, we have the same program. Today's subject is lightning and atmospheric event, basically the basics of lightning protection. Then we also discuss about the details of hazard due to lightning and basic protection of humans on 29th May, protection techniques of buildings based on the standards on 5th June. Some important points of non-standard products or non-standard systems and methods on. Sorry, it's not 25th June, it's 12th June. My mistake. Sorry for that. The programs in the classes will be taken by Dr. R Nagabhushana. I would like to introduce a little bit about our program, VIDYUT SURAKSHIT BHARAT ABHIYAN, and Dr. Nagabhushana. Then we will hand over the mic to Dr. Nagabhushana for the presentation. Now, the program VIDYUT SURAKSHIT Bharat Abhiyan, basically it is All India Awareness Campaign, which we organized or which we are organizing. Organized by CISSA, Center for Innovation in Science and Social Action. Under CISSA, we have an organization called LARC, Lightning Awareness and Research Center. An NGO based out of Trivandrum, having a lot of activities on science-related subjects. One of the activities is LARC, Lightning Awareness and Research Center. And CISSA is also a regional center for excellence acknowledged by the UN University, United Nations University for sustainable global goals. All of you are aware of sustainable goals. So we are an accredited or acknowledged center for excellence. We took the subject of electrical safety because here all of you are aware that almost every day accidents are happening across India. And so many accidents are happening and a lot of people are getting affected. Hundreds of crores of rupees worth properties are getting damaged, and it's actually a serious issue for our nation. In the chart, what you are seeing is presentation, taking a paper, a study report published by one this gentleman from Japan. He presented a paper in the National Workshop on Electrical Safety on 12th April 2016. According to his paper, in India, about 723 people are getting killed because of electricity-related, especially the shock-related problems out of 100 million population per year. You can also see the comparison of the other nations. We are actually too much ahead of the other nations. Of course, you also should think that all the accidents in India are not reported. This 723 is from the reported accidents. The same study report they have made the electrical safety situation. A survey they made about the knowledge and other, the systems followed in several countries, and India got the least score out of the G20 nations, 16%. So if you look at the number of accidents happening, and if you look at the data, which is the study reports available, you can be sure that the situation is not so good. This is the reason we started this particular subject, and we started electrical safety, especially for industries and residential purpose, because most of the time accidents are happening in low voltage. There is a data out of 100 accidents, almost 50 plus percentage happens on the low voltage system, about 43 or so happens on the distribution, and only 2% happens on the high voltage system. So our focus is towards the low voltage and the distribution system. We have selected few points, few subjects, and we were continuously making 2 hours classes weekly, 3, 4, 5 classes, and I'm happy to say that we have completed, or we are going to complete almost 100 classes in the next weeks, which was our target. For electrical safety, we have a group of experts supporting us, starting with Mr. Appavu. He is the retired chief electrical inspector from Tamil Nadu. Then Mr. James Kutty, Mr. Vinay Nagdio, retired from electrical inspectorates. We have Mr. Patnaik, general manager from OPTCL. Mr. Goswami was also retired from the Bureau of Indian Standards, a senior officer from BAS. Then Mr. Mittal and Mr. Srinivas. So these engineers were supporting us for the program. Now, one of the subjects we also took up along with the electrical safety is lightning protection. You can find the details from our website. We have a website, VIDYUT I'm just showing the website. We have a list of advisors starting with Dr. Shashi Kumar. But before that, I would also like to inform you that the lightning awareness activities of CISSA or LARC, this is not new. We were doing it since 2006. In fact, Dr. Nagabhushana visited or traveled along with us, taking classes in several cities, of course, several occasions. We have also a group of experts from India, including Dr. Nagabhushana. Also, we have a group of experts, international experts, those who are supporting us to frame the technical part of the presentations or the technical study materials and all. So we also have a blog in the website, VIDYUTSuraksha.com. You can go to the blog and a lot of information. Actually, we started building up the blog. Only few information are there at the moment, but slowly on daily basis, we are uploading data. Our program is supported by the Bureau of Indian Standards, also by several organizations. Unfortunately, this is a mistake, except the National Safety Council. All the other organizations are supporting us. So our aim is to make a safe, nation. Now, regarding today's program, as I said, we have Dr. Nagabhushana. Dr. Nagabhushana, in fact, one moment, I have to make some small arrangements. Dr. Nagabhushana is formerly professor and the chairman of the High Voltage Department, the High Voltage Engineering Department in Indian Institute of Science, Bengaluru. And he is presently the professor emeritus of MSR Institute of Technology in Bangalore. He has completed his BSc in Mysore University, then BE, ME, and PhD from IISc. He is a fellow of the National Academy of Engineering, and he is an award winner of the Prime Minister's Academic Excellence Award. He has joined his activities related to lightning in 1963. He joined as a faculty in Department of High Voltage Engineering in IISc Bangalore, and he was placed in charge of the lightning arrestor laboratory, and he was the main person behind development of nonlinear resistors for lightning, the surge arrestors, the high voltage surge arrestors. From 1965 onwards, he has been dealing with the various aspects of lightning and protection from lightning of transmission lines, satellite launch pads, for example, ISRO, then power equipment and insulation coordination of the high voltage system. 1989, Aeronautical Development Authority, they have of the DRDO, gave a project for the design, fabrication, and commissioning of a lightning test facility in Bangalore for testing the, the light combat aircraft and the other products of the ADA. So this test facility was having 4 million volts impulse lightning generator. Also, this facility can provide or produce 200 kiloamperes, 100 kiloamperes, and 20 kiloampere and 200 amperes of impulse, lightning impulse current. This is one of the unique facility across the globe. Probably if you have visited the Bangalore airport, the old airport, this facility was on closer to the runway. On one side of the runway, we were able to see it not in the new airport, but in the old airport. Now, this facility was, even today, it is used for testing and evaluation of the lightning performance of the LCA aircraft, Hansa aircraft, and other aircraft components of Hindustan Aeronautics Limited. So this is the background of Dr. Nagabhushana. By this small introduction, I would like to invite Dr. Nagabhushana for the presentation. Before that, I would like to introduce one more gentleman, Dr. Pradeep Dikshit, Professor Dikshit from the Electrical Engineering Department, MSR Institute of Technology, Bengaluru. He is also supporting us in our activities related to lighting. So now, welcome and over to you, sir.
Good morning to you. Good morning to everyone here. At the outset, I think I must really place on record the appreciation of every one of us to Gopakumar for the tremendous efforts he and his team are doing to make the country lightning resilient in the true sense, in the real true sense. It's very important because there are many other people who pretend to work on that, but without really a full knowledge of that. In fact, I'm really grateful to Kumar also for giving me this great opportunity of sharing whatever little knowledge I have got with all the attendees and the others also. I'll be very happy to tell you that this will be more like a detailed discussion matter. Therefore, even though I talk a lot, the emphasis will be on the discussions so that it's knowledge that is transferred, it's not simply the portion that is covered. So let me start. Lightning is one part of the atmospheric electric phenomena. It's a very frequent, spectacular, natural electrical phenomenon in the atmosphere. Close-by strokes can be extremely scary and extremely dangerous. I'm sure everyone would have seen the lightning hundreds of times, most of them far away, maybe kilometers away, very rarely close by. But when it happens very close by, even if one is inside a building, residential building or whatever, it can be very scary. The sound can be really very scary. And very often, sometimes, the glass windows are broken because of the thunder, that's the sound itself. Lightning has got very considerable destructive potential, and it has attracted the attention of many people all over the world to think of protective measures to prevent these things. Firstly, severe fire hazards, which includes damages to buildings, tall trees, and many other things indeed. Injuries to humans and animals, of course. Our main interest is in humans, but animals also die because of the lightning occurring. They'll be wandering in the open fields, under the trees, etc. They are subject to a lot of injuries or even deaths, fatalities very often. The fatalities in India seem to be between 2,000 to 3,000 per year. Now, this is, I should say, with some regret, that there's no formal record of these things in India. A formal record must include, for example, the name, his activity at the time of being struck by lightning, whether there was an injury or straight away a fatality, what was the type of injury. These are not properly recorded. A record like that, and if properly published periodically, it would be of great help to arouse the interest of people to avoid these things much more. Now, the fatalities apparently is the highest due to all natural disasters in India, at least, definitely. In USA, by simple education, cost-free almost, simple education, the death rate has come down by a factor of 10. Whatever was hovering between 300 to 400 deaths per year has come down to approximately 30 or less per year. Simply education, nothing else other than that. Now, lightning and its electromagnetic fields can damage sensitive electronics if not properly shielded. So it can be sensitive electronics inside residential buildings, aircraft control systems on the ground, or the aircraft electronics in the aircraft itself. So these are having very serious consequences from failures of electronic equipment, down around right up to fatalities. Go further. Now, what are the electric phenomena? In fact, instead of giving the title as lightning, I have made atmospheric electric phenomena. The reason is that lightning is only one part of the atmospheric electric phenomena, which are all very, very interesting. But unfortunately, all of them have not come to the notice of the public, but they may not be hazardous, but it will be interesting to know. One is, there are three types of lightning. Lightning inside the clouds, or what we call intercloud lightnings, intra-cloud lightnings, and there can be cloud-to-cloud lightning and cloud-to-ground lightning, which is the most hazardous. And then above the clouds, lightning occurs within the clouds and below the clouds, but above the clouds, there are events which we call transient luminescent events, which is shown in this picture. There are what are called blue jets. Can you see this? Okay, these are blue jets. And then we have got sprites. These are sprites. These are elves. This tail-like structure, they are called tendrils. Now, these are all very huge in dimensions. The elves can spread for several hundred kilometers. That's the surprising thing, because people started observing it closely only from 1960 onwards, roughly about 50, 60 years ago. Whereas lightning was first shown as an electrical phenomena by Benjamin Franklin in 1752. Nearly 300 years ago, these transient luminous events have come into observation only from approximately 1960. That's roughly about 60 years ago. Subsequently, many studies have been made. Why many studies have not been made previously is that they were not seen very clearly. Only the aerospace vehicles in the relevant atmospheric level have observed this, and they have immense keen interest, and they have come across all these atmospheric events. These are all associated with lightning. Whenever lightning occurs cloud to ground, these can also be triggered. Now, these are very beautiful colored, very huge in dimensions, and then they accompany, rather they are very important parts of the atmospheric electric circuit. Oh, to understand the various things, we'll first of all see the various atmospheric layers. The first layer, in which we are all there, ground level to approximately 10 kilometers above mean sea level, is known as the troposphere. 99% of the water vapor of the entire atmosphere is present in this region. 99%, that means almost the whole lot is present in this region. The air pressure and temperature in this region drops with increasing height. Ground level can vary from 0 degrees in the Arctic, for example, sub-zero. In the tropics, it can go up to 30, 40 degrees centigrade. But as we go up in the atmosphere, the temperature goes down typically to 0 degrees Kelvin, 0 degrees centigrade, 0 degrees centigrade, around 3 to 4 kilometers above Earth's height, above the mean sea level. And then above 10 kilometers is called the stratosphere, approximately from top of the troposphere to 50 kilometers above mean sea level. This is mainly containing ozone in a large portion. The high energy UV light from sun produces considerable ionization in this region. This is a very important phenomena as far as lighting is concerned. It produces a lot of what we call ionization. That means dissociation of the neutral molecules of air, nitrogen, oxygen, etc., into ions in a substantial proportion. The temperature in the stratosphere goes on becoming warmer with height. It lacks turbulence and updrafts. Because of the lack of turbulence and updraft, it's a very attractive zone for commercial aircraft to fly. There will be no turbulence. The flight will be quite comfortable comparatively. In the troposphere, there can be a lot of turbulence which can be felt by the aircrafts, and therefore can be very risky also. That's why most of the commercial aircrafts take to the stratosphere region for flight, for the major port of the flight. Then we come to the mesosphere. It's above the atmosphere, above the stratosphere. up to about 85 kilometers above mean sea level, the temperature gets to minus 90 degrees centigrade at around 85 kilometers. The pressure is very, very low, approximately 1% of the atmospheric pressure. The standard atmospheric pressure is 760 millimeters of mercury at the mean sea level. That means the pressure is around 7.6 millimeters. 760 millimeters, 1% of that is about 7.6 millimeters. Is what we call in vacuum terminology as a soft vacuum. In this region of pressures, electrical discharge will be what we call glow discharges. What happens in tube lights, typically. Tube lights, there's a low pressure discharge or a glow discharge. Above the mesosphere, we have got the thermosphere, above 85 kilometers, and then the temperature here goes up to 2000 degrees centigrade. But in contrast, that what we can also say is air is very, very thin. It feels extremely cold. Now, why is this contradiction? We say very high temperature up to 2000 degrees centigrade on the one hand, and we say it feels very cold. Remember, temperature is a direct measure of the energy of the molecules in the air. Therefore, whatever molecules are there in the thermosphere, they are very, very energetic. But the so-called mean free path of this will be in hundreds of meters. That means if a person stands there, the air molecules will not collide with him frequently at all. So he's not able to feel the energy of these molecules. He feels only the coldness of the atmosphere at that temperature, in that region. Therefore, because of this, we say it feels very cold. On the other hand, the energy is very high, 400 degrees centigrade to 2000 degrees centigrade. The contrasting statements, this is the explanation for that. Then we have got the highest layer of the atmosphere, exosphere, is probably the final frontier of the Earth's surface, Earth's gaseous envelope. It's extremely thin. The so-called mean free path, or the distance between successive collisions of the air molecules, can be in kilometers, not meters, not centimeters, not even kilometers. It can be many, many kilometers. It is extremely thin. It leaks into outer space. The top of the exosphere is variously estimated to be 100,000 kilometers to maybe 190,000 kilometers. So this is exosphere. These are the overall thing. But for interest to us, from the lightning point of view, is what we call the ionosphere. This ionosphere is a very important parameter in the phenomena of lightning, particularly the lower ionosphere, about which I will be mentioning just a little later. Ionosphere happens to be what we call the positive electrode of the global capacitor. We will be talking about the global capacitor in some more details a little later. Ionosphere is not a distinct layer by itself. It's a mixture of a few other layers. It extends from approximately 85 kilometers above Earth to approximately 500 kilometers above Earth. The estimated electrical potential or the voltage with respect to Earth is not a small number. It's 250,000 volts, 250 kilovolts to approximately 300,000 volts. That means 300 kilovolts. Remember, it's a huge voltage, and the lower atmosphere in particular has got this potential nearly constant with respect to Earth. That means Earth is an electric electrode with respect to Earth. This lower ionosphere is at a high potential, positive potential of 250 kilovolts to 300 kilovolts, which is nearly constant. Now, this high voltage here induces negative charges on the Earth's surface. It induces negative charges on the Earth's surface. The lower ionosphere, about which I mentioned as an important part of the lightning activity, extends from approximately 50 kilometers above Earth to 75 kilometers above Earth's surface. We call this the global capacitor, about which we'll see a little later. The lower ionosphere is also known as the electrosphere because of the electrical charge and the charge domain. Now, this is the picture of the so-called global capacitor. It is not really to scale. I have shown Earth and then the lower ionosphere. This is the Earth, of course, with negative charges on the surface all around, everywhere, induced by the positive charge in the lower ionosphere. This is the lower ionosphere, which is positively charged because of solar radiations, ultraviolet radiations, cosmic radiations etc. It's ionized, and then it has got large amount of positive charges, and therefore it is the positive electrode of the so-called global capacitor. So you'll see that Earth is the negative electrode, and the lower ionosphere is the positive electrode of this capacitor, which we call as the global capacitor. Now, not to scale again, the cloud is shown here, typically around 2 to 3 kilometers above Earth's surface, up to about 10 to 13 kilometers above surface. Obviously, not to scale. Don't get worried about this dimensions. I have to make it clear to be seen by the audience. Therefore, I have shown it a little big. It will be just a line, nothing more than that. Above the Earth's surface, above the cloud, we have got a region where we have got the so-called transient luminous events, which were shown a little earlier. The sprites, the blue jets, tendrils, and the elves, they occur in this region. In fact, together, these cloud charges and the elves together take positive charges to the lower ionosphere. We'll be discussing about that much later, but we'll see this positive voltage of 300 kilovolts above Earth's surface is nearly constant. It varies between 250 kV to 300 kV. Sometimes there can be more fluctuations. Area-wise, there can be fluctuations. It may be more here, it may be less here. All these are statistical. Similarly, Earth will have negative charge. The charge density may be varying from point to point. We have got soil, we have got mountains with ice, we have got seas. So everywhere there can be variations. We can give the typical characteristics of these global capacitors a little later. Now, this global capacitor plays an extremely significant role in lightning and the transient luminous events. The characteristics of the global capacitor are now mentioned in this table. Now, to summarize the whole lot, the lower ionosphere, which we saw just a little while ago, is nearly 250 to 300 kV, nearly constant voltage with respect to Earth. Earth is the negative electrode. So this is the global capacitor. Now, the average leakage current now is about 3 into 10 to the minus 12 amperes per square kilometer. The usual terminology in electroengineering is that it's 3 picoamperes per square meter. Now, if you take a metal sheet of, let me say, 4 meters by 4 meters, mount it behind our backyard and ground it through a picoammeter, we can measure some 50 picoamperes. Anywhere approximately maybe 30 to 50 microamperes, 60 picoamperes, you can measure it. So that shows you, yes, this is true. There's an average leakage current right from the ionosphere to the ground, and leakage of current from the lower atmosphere to ground. Now, the average charge density on the Earth's surface is approximately about 1.1 to 10 to the minus 9 coulombs per meter squared. Now, if you take the ratio of the voltage, 300 kilovolts, okay, I will come back to that again. The average current density I have shown you is 3 picoamperes per square meter. If you consider the whole Earth's surface, multiply the current density by the total surface area, the total leakage current will be approximately 2,000 to 3,000 amperes. This current leaks from the lower ionosphere to Earth. Why does it leak? It's a very interesting question. If air is a very good dielectric, ideal dielectric, this current will not come into picture at all. But the atmospheric air is getting ionized by the cosmic radiation, solar radiation, ultraviolet rays from various sources. It gets ionized. Every second, approximately 6 to 12 electron-ion pairs are created because the interaction of this cosmic energy with these neutral molecules of the air, that means nitrogen, oxygen, etc., all the gases, they get ionized. 6 to 12 electron-ion pairs are created. So this forms this helps to form the current. The positive charges come down to Earth, the negative charges go to the atmosphere, the lower ionosphere. So that forms the leakage current. So if you measure the total leakage current, that's the ratio of the voltage to the current, the ratio of the current voltage to current, use the effective resistance of the global capacitor insulation, so-called insulation, Earth to lower atmosphere, lower ionosphere. The resistance is approximately 100 to 150 ohms, which is here. Now, next thing is, what's the electric field at their surface? Remember, the potential of the ionosphere, lower ionosphere, is around 300 kV. Earth is a negative electrode. So what's the electric field at the Earth's surface? Typically about 3 volts per centimeter. So if you think of a man, approximately 1.5 meters tall, from head to foot, there will be approximately 4.5 volts. It's a very small voltage. It will not be sensed much because the current is too low, and the human body also acts as a near short circuit for these currents. The impedance of the earth instead of the air around the person is much higher than the impedance of the body. Therefore, it nearly acts as a short circuit. The voltage is not felt really. Sorry, I made a small mistake. 3 volts per centimeter, that means 300 volts per meter. If you think of a 1.5 meters tall person, it will be 450 volts, which is a substantial voltage, but still the person does not sense any electrical shock because the current is very, very small. That is 3 picoamperes per square meter. A human person may be equivalent to approximately only 0.1 square meter. That means the current is extremely small. I must mention here that the electric shock is mainly due to the current, not the voltage. The voltage drives the current. It's the current which creates all the sensations, as we'll see a little later. It's always the current in the lightning which is a damaging feature. Current is the damaging feature. Current is a damaging feature. You can emphasize it many times. The voltage is the one which drives the current, but it's the current which causes the damages. So now, if you think of the lightning developing the ground from the cloud to ground, which we'll see a little later, typical field on the Earth's surface goes up to about 400 volts per centimeter to approximately 600 volts per centimeter, just before the lightning reaches the ground. Now, the average equivalent current per lightning stroke is 2 amperes. Now, supposing this leakage current flows continuously, the capacitor must get discharged. If you take any capacitor or even a battery and short it, the voltage gets completely driven down to 0 in a very short time. So why does this lower atmosphere remain at 300 kilovolts in spite of this huge leakage current of the order of 1000 to 1500, 2000 to 3000 amperes? It's continuously flowing. Why does not this global capacitor discharge and the voltage goes to 0 in a very short time, maybe a few seconds? The phenomena which recharges this global capacitor, one of the major phenomena, is lightning. So lightning is nature's phenomena of recharging the global capacitor and retains the potential of the lower ionosphere approximately between 250 kilovolts to 300 kilovolts. I hope this point is very clear. There's a very important thing because lightning is now nature's phenomena, one of the major phenomena of nature, which recharges the global capacitor so that it remains at a near constant potential of 250 kilovolts to 300 kilovolts. Now, estimate total number of lightning that takes place in the world per second is 3000 to 5000 strokes per second. The average equivalent current of lightning stroke is only 2 amperes. 2 amperes. So these are the major characteristics, electrical characteristics of the global capacitor. So now we will see what's the importance of lightning. Of course, now we'll go into the other aspects, the lightning, how it develops and things like that. But these are the basic features of the electrical phenomena of the global, I should say, global electrical phenomena, atmospheric phenomena, of which lightning is only one part. But it plays a very important role of maintaining the potential of the global capacitor nearly constant at 250 to 300 kilovolts. I think this summarizes this basic feature of the global electrical system. Now we'll go to lightning proper. I have already talked about these points earlier. Continuous leakage current 2000, 3000 amperes. Potential of the atmosphere goes 0 very soon, but is sensibly constant. Lightning is the major mechanism of making for this loss of charge or potential of the ionosphere. Now it's very similar to what we can call the Van de Graaff generator, where charge is sprayed onto a belt which is driven up by a motor, so the charge is taken up to the upper electrode. Here is the solar energy which gives the energy for the charges to go up from the Earth's surface to the lower ionosphere in a very, very, very fantastic sense. We'll go into the details as we go further. So now the next topic is lightning phenomena. How does lightning take place? We have said that lightning is nature's means of keeping the lower ionosphere charged at 300 kV, nearly 300 kV constant. But how does it happen? Now, the preliminaries regarding this phenomena is as follows. Lightning was demonstrated as an electrical discharge by Benjamin Franklin by his very, very famous kite experiment as far back as 1752. How did he demonstrate it? During a thunderstorm weather, when there was mild rain, he was flying a kite, standing himself under a portico, so he was not getting wet, but the thread with which the kite was supported was getting wet. He saw that the wet thread gave rise to electrical sparks at various places, particularly downward regions. There were electrical sparks which were very similar to the sparks seen elsewhere by other electrical experiments at that time. So these sparks seen on the wet supporting thread of a kite showed Benjamin Franklin that lightning is an electrical phenomena. Now, after this very important fundamental confirmation that lightning is an electrical discharge, much work was carried out for over more than a century to understand it. Much work has been carried out, is still going on to understand it fully. I should say at this moment also, we will see it a little later. There have been several theories, maybe even 7-8 theories have been proposed to explain the phenomena of lightning, electrification, etc. But not even one has been fully satisfactory by itself. So it's a combination of several physical phenomena that leads into the formation of thunderclouds and lightning. So now, the important thing for us to note is that lightning does not occur all around this year. It happens mostly in a certain season. So only under certain conditions, under certain atmospheric conditions, a cloud forms and gets electrified. That's the most important point. The cloud forms and gets electrified. When the electrification is adequate, initially electrical discharges occur within a cloud. That happens first. As we'll see a little later, electrification is very high within a cloud and the electric field will be very high within a cloud. So we call that intra-cloud lightning or internal lightning. Now, if there are discharges between adjacent clouds, they are known as cloud-to-cloud lightning or intercloud lightning. If the electrification of the cloud proceeds much further, the charge collected within the cloud, top, bottom, and negative bottom, will be growing so high, the electric field intensity becomes sufficiently high to initiate discharges from the cloud to the ground. That's what we call the cloud to ground lightning, which is of the greatest importance in the present webinar. Now I have shown pictorially here in a very crude way the intra-cloud lightning, which is within the cloud. See right here, this is the negative region, this is the positive region, there is a discharge between the two within the cloud. This is called the intra-cloud lightning. So you think of two clouds adjacent to each other. They will not be so very isolated as shown by the figure, but they'll be adjacent to each other. They are spreading out to a thin cloud, and then electrified regions are there, non-electrified regions are there like that. But there can be an electrical breakdown and a huge discharge path between the negative region of one and the positive region of the other one. We call that the intercloud lightning like this. Intercloud lightning between the negative charge region of one cloud to the positively charged region of the second cloud is the intercloud region. Now I must point out here that the intracloud region within the cloud and the intercloud lightning between the two clouds can be of great danger to aerospace vehicles like the aircraft, helicopters, etc. So therefore, they will have to avoid this type of weather when lightning takes place. Why should they avoid? Because of the currents which are huge, and the effects can be very disastrous, as you will be seeing presently. Now, how does this lighting happen? We have seen that intra-cloud, inter-cloud, cloud-to-ground, 3 types of lightings we have classified. But how does it happen is the important question that's facing us today. Now, the important point to note is that solar energy is the main energy which does all this phenomena possible. The solar energy heats the Earth's surface layer. It evaporates the moisture from this Earth's surface, and this moisture enters the air layer in contact with the Earth's surface. So we have got a moisturized air in contact with the Earth's surface. Now the Earth's surface also heats up the air in contact, and of course the moisture which is inside that air. Therefore, now we have got air plus moisture which is hotter than the upper regions. And then also invariably there are very fine dust particles present everywhere in atmosphere. They are known as aerosol particles. Very fine dust particles are known as aerosol particles. So on top of the Earth's surface, which is heated adequately, we have got hot air plus moisture plus aerosol particles. This moisture plus aerosol particles and hot air, because they are hotter than the air above them, it starts moving up. It starts moving up and up. We call this the updraft. So the updraft contains hot mixture of air, moisture, and aerosol. As it moves up, we know that the temperature drops down continuously. It was shown earlier in the troposphere. Temperature goes down from Earth's surface to 0 degrees, nearly around 2 to 3 kilometers above Earth's surface. So as the updraft moves up and up, it gets cooled down. The moisture starts condensing when it approaches 0 degrees centigrade level. That means approximately 2-3 kilometers above level, moisture starts condensing. It condenses, of course, into very, very small ice or water droplets. They are known as supercooled water droplets, very, very fine droplets. They're also very likely to be thrown up, rather moving upwards. So what we have above the 0 degrees centigrade is, in addition to normal moisture, we have got moisture plus small amount of condensation into water. Here I must point out one very interesting thing. Suppose we have got absolutely pure water, absolutely pure, no dust particles, whatever. When does it freeze? The question is very easy, one may think. It's not so easy. The temperature at which the pure water freezes is around -30 to -40 degrees centigrade. It is not 0 degrees centigrade or 4 degrees centigrade. It's because of the presence of these aerosol particles. When we cool down to approximately 4 degrees to 0 degrees, the moisture starts settling around these dust particles, and that's how the condensation starts and goes further. If there are no dust particles, the freezing takes place only around -30 to -40 degrees centigrade. So now we have got around 2 to 3 kilometers height an updraft containing hot air, moisture with some amount of condensation, and then aerosol particles. Now this continues as we go further and further up. The very, very fine water droplets, they grow in size. The surrounding moisture settles on the superfine water droplets. They grow into larger and larger drops. And then the temperature goes down much below. As you go further higher up, they will freeze into small icicles. Initially icicles, very small ice particles, which grow into what we call hailstones. So we have got now superfine water droplets, larger water drops, icicles, and around 14 kilometers hailstones are there. Now, once the large water droplets and hailstones become sufficiently large, the gravitational force attracting them downwards will make them fall down. So now the cloud has got an updraft consisting of hot air, moisture, aerosol particles, going on the icicles, slightly condensed moisture going upwards, and then downward moving large water droplets, supercooled water droplets, and hailstones, they are coming down. So it's a very interesting picture within the cloud. It is shown here. The red letters show the mixture that's coming down, hailstones and large supercooled water droplets. Upward, we have got various levels of moisture, fine drops, dust, and then less moisture, more water drops, then water droplets here, and then more and more icicles, supercooled large water drops, dust again, hailstones and large supercooled which are coming down. Now this formation of upward and downward drafts gives the main zone of electrification, which takes place mostly in this region, where these two are mixing in a very, very rapid manner. The electrification takes place here. Now, as I told you, many theories have been proposed over more than a century how electrification occurs in this mixture of upward air draft, moisture, supercooled water droplets, air, downward large water drops and hailstones. Now, Simpson's theory, Elster-Geitel's theory, Wilson's theory, go on. In fact, I think Madame Curie also has developed some theories of Uppsala University. He is very much there, active in University of Uppsala even today on lightning itself. Now, no one theory is adequate. Therefore, we will not try to go into the theoretical aspects of that. Some of them can go into quite a bit of mathematics. Therefore, I will rather avoid going into those things. What we have is this important feature is the cloud top essentially becomes positive. Top zone is not a point. Top zone becomes positively charged. The middle to almost bottom gets negative charged, and then as we go down towards the bottom of the cloud, the negative charge concentration becomes more and more. It is shown in this figure 5. So you'll see I have just drawn a line in the middle, but there's nothing rigid about it. You'll see the top half, top zone. I'll not call it top half, it is the top zone, is having a larger percentage of positive charges and some amount, very small amount of negative charges. And then bottom zone has got a much higher concentration of negative charges and also some positive charges. And the most important thing for us to note is that the negative charges in the bottom cloud attracts positive charge from the air surrounding, and there will be a zone of small positive charges present here. The zone of positive charges below the bottom of the cloud and the high concentration of negative charges within the cloud, they are the most important from the point of view of initiation of a lightning. Now, the question is, how does the lightning get initiated? Now, the typical electric field required for breakdown of air into a spark or an arc, whatever it is, at the Earth's surface is approximately 27 kV DC per centimeter, or approximately 3 kV per millimeter at the Earth's surface. However, inside the air, we find that the electric field intensity is only of the order of about 10 kV per centimeter to about 4 kV, maybe 1 kV to 4 kV per centimeter, which is very, very low. So discharge cannot happen within a cloud. Therefore, more recently, there has been photographic evidence also. Lightning gets initiated in the bottommost region. That's what I mentioned to you here, in the bottommost region, what they call bidirectional leaders. We'll talk about it presently. We'll go further now and see how it goes on. As I mentioned to you, the field within the electric field within the cloud is 100 kV per meter. That means 1 kV per centimeter to 2 kV per centimeter on the average. And it can go right up to 4 kV per centimeter as shown here. But this is not at all adequate for breakdown to occur. Now, recently, field photography has shown that streamers are electrical discharges. I will explain to you what streamer and what's the leader a little later. The streamers, that means discharges start between the bottom zone of the negative charge and the positive charge zone immediately below the cloud bottom. As I shown you in the previous figure, that's the figure 5. This is the bottommost region has got some positive charges induced by the negative charges at the cloud bottom. Discharges start occurring between these two. And because they are spread horizontally, these discharges spread sidewise, maybe even up to 100 kilometers. Not a small distance, not a small distance at all. So these discharges spread in both directions because they are both horizontal. They are spread in both directions. They are therefore known as bidirectional leaders. Now there's a small distinction, important distinction between what we call a streamer and a leader. In a streamer, the development of electrical discharge is due to ionization by the electrical field. Mainly, the electrons collide with the neutral molecules and then cause an electron to get ejected. So that will create an electron-ion pair. This is known as ionization by collision. This is a very well-known phenomena, particularly in hydro engineering. It's a very fundamental phenomena, ionization by collision. So this is a streamer where the electrical discharge development is primarily due to the applied electric field and due to collision between electrons and neutral molecules. That's collision by ionization by collision is the prominent phenomena. On the other hand, once this current density in the streamers become very high, there will be high temperatures developed. In high temperatures, there will be thermal ionization, and that becomes much more prominent than the ionization by collision process. This is known as a leader that can develop by itself, providing the electric field is adequate for its propagation. That's a leader. So this is a distinction between the streamer and the leader. Now, as I told you, between the negative charges of the cloud bottom and the positive charges of the below the cloud bottom, these streamers develop into what we call bidirectional leaders. Now, one end of this bidirectional leader, essentially the negative end, starts developing towards the earth. So one end of the bidirectional leader starts developing towards the earth. Now, this is the initiation of the lightning. This leader moves towards the earth. That's the most important point. Now, why does it develop as a one shot to the earth? No. The reason is the moment this leader develops over a short distance, the charge density at its tip falls below the level that's necessary for its development further. So what happens is that it will wait. In this waiting period, very short time, they're all in sub-microseconds. 1 microsecond is 10 to the minus 6 seconds. Sub-microsecond time is required only for the parent cloud to feed the charge into the tip. And once the tip is fed with electrical charge, the electric field at the tip increases and it progresses further. So this is what we call a stepped leader. So earlier, people thought the development of the leader takes place within the cloud like this. But more recently, as I told you, photographic evidence, which I think I have got photographs of that also, is between the positive region and the negative regions here. They develop into bidirectional leaders shown here, and that develops towards the earth. Remember, this is the negative charge. Now, there's a very interesting question which may come up in your minds. Because of the normal electric field, the charge on the earth surface is negative. So how can this negative charge come towards the negative charge? We know very well by Coulomb's law, like charges repel each other. So how does it develop? It's a very interesting question. The lower ionosphere has induced negative charge all around. The charge density I have told you is approximately 10 to the minus 9 coulombs per meter squared. But as the negative charges gather in the cloud bottom, that induces a positive charge on the earth's surface. Please remember this again. It is worth repeating that. As the negative charge develops within the cloud bottom here, that induces a positive charge on the Earth's surface below the cloud. So elsewhere, far away from the cloud, the Earth charge density will be negative. But right below the cloud, the charge density on the Earth has turned to from negative to zero, zero to now positive. So now you will see that the streamers are facing the, rather, they are getting the charge fed from the parent cloud. Negative charge is fed to the step leader, and then the positive charge is there on the Earth to attract it, so it starts developing downwards. As I told you, this development is only in steps. The reason again I will repeat, it's worth repeating that when the charge is sufficient, when the electric field intensity at the tip of the leader is sufficient, it develops further down, but as it develops down, the charge at the tip comes down, the electric field intensity at the tip therefore comes down, and therefore it cannot propagate further, it holds. In the meanwhile, the huge negative charge available in the cloud bottom, right up to 100 coulombs will be there, so that is fed to the tip through the conducting channel of the leader, step leader, and then once the step leader gets this charge, the electric field starts building up once again. Once the field comes up to the required level, there will be further breakdown, so it takes the next step. So this leader towards the Earth develops in steps. Now just a small deviation, whether it's intra-cloud discharge or cloud-to-cloud discharge or the cloud-to-ground discharge, the development is always in a stepped way, stepped leaders. So when you observe lightning, you would have seen it's not a single line. It goes up in steps, sometimes very, very crooked also. Why is it branching off? That's another interesting question. Why is it developing into steps like this? Now, supposing it has come to a certain point, any one point here, now at that point, it will see the air all round. The electric field density for breakdown of this air all round will not necessarily be the same. The electric field breakdown strength for the air will be different in different directions because the air is not as homogeneous as we think. But at the minor level, at the sort of very small level, the electric field density will be different. So breakdowns can occur in a very different direction from the previous step. Therefore, it can develop into this direction, and sometimes the breakdown can take place in multiple directions also, because in the multiple directions, the electric field strength of the air can be weak. Therefore, it develops in multi-directional ways. So now you will see that what we have seen in the real life, what we have seen, most of us would have seen hundreds of times or maybe thousands of times. It develops into many, many steps like this, but on the whole, it starts moving towards a tall grounded object on the Earth like this. Why? The question is very easy to answer. Now, as I told you, the negative charge here on the cloud induces a positive charge on the Earth's surface also. The same is true of the tall grounded objects. I'm sure you recall that if you have got a large size arbitrary-shaped conductor and it is given a charge, the charge density is inversely proportional to the radius of curvature, which means that the sharper points will have higher charge density, and because of the higher charge density, the electric field intensity at its surface will be higher. So now, if you think of a tower, the tallest point of the tower is the sharpest point. Therefore, the electric field intensity there will be the highest, and therefore there will be local streamers. Again, remember streamers, because here the current growth is by ionization by collision phenomena. It's not yet thermal. Therefore, we call it a streamer. Whereas here is a stepped leader. It is temperature dependent there now. Temperature is the driving force in addition to the electric field. Here is only the electric field. It's a streamer here. The stepped leader here. They start moving towards each other. In fact, different branches can move in different directions. There is one more object. It can go towards that also. So as the stepped leader comes down, the electric field intensity becomes higher and higher and higher. The reason is this gap between the positive electrode and the negative electrode becomes shorter and shorter. The potential of the cloud, as I mentioned in an earlier table, can go right up to 100 billion volts. Now, the minimum potential required for a lightning to occur is approximately 2 to 5 million volts. So you can say that the potential at the tip of the step leader may be anywhere from a few million volts to maybe tens of millions of volts. Therefore, as this leader comes down, it's easy to imagine the electric field density becomes higher and higher in this direction. Therefore, it starts going towards it finally, and then attaches it to itself. So we call that a forward leader between the cloud and the grounded object. This is called the forward stroke. It's essentially the step leader coming into contact with the streamer from the grounded object, which completes the forward stroke. I have shown it here. You see that there are two other branches which are very close to ground, so it may attach here also. It may attach here first, it may attach here also. Now, some of the properties of this are very important. The velocity of development of the step leader is about 1/10 the velocity of light, approximately 1/10 the velocity of light. It is relatively slow because it develops in steps. It has to wait for the charge to be fed from the cloud to the tip of the step. Now, once the step leader makes contact with the earth object and the forward stroke is complete, it behaves as a near short circuit between the huge voltage of the cloud and relatively zero voltage there. That means the huge voltage is applied between these 2 points and there is an effective short circuit between these two. Now what happens because of this is a very huge current develops in the same channel, extremely huge currents which can vary anywhere from 4 or 5 kiloamperes right up to 200,000 amperes. That means 200 kiloamperes. And the channel diameter is hardly of the order of 10 to 12 kilometers. The current flowing in that small region heats it up to enormous temperature to the order of about 15,000 degrees Kelvin to almost 60,000 degrees Kelvin, which is comparable to the temperature of the sun's surface. So you'll see that it becomes extremely hot, extremely bright, and then it heats the surrounding air very rapidly because the high temperature, the air expands at a very rapid rate. That's what you hear as the thunder. That's the acoustic effect of the thunder. So we have got first the forward stroke, then the return stroke causing the thunder. Thunder means the sound because of the supersonic velocity of the air expansion in the surrounding area. So now here are the figures showing the bidirectional leader. The bidirectional leader has really developed somewhere in this region. See, time-wise development is here. It's very interesting to see that it's just a very small one to start with here. It has developed bidirectionally here. It's here only, it looks to be a very small spot. It may be a few meters. This may be a few tens of meters wide. Now you'll see that this side has become brighter. It is traveling towards the earth. Here again, it's traveling towards the earth. Behind it has become less bright. Here brightness remains. It has been shown in a graphical way here, but it may be not very clear. But that has been shown here in a more detailed way. Shown that here the forward stroke is complete now. I have shown it as a very broad one. As I told you, this was the original thinking. It will happen somewhere within the cloud. I cannot say it will not happen there, but majority of the cases is the bidirectional leader which develops at the bottom of the cloud between the bottom negative region and the positive region between that develops into a bidirectional leader, then develops towards the earth, becoming a step leader, and then joins streamers on the top of the top grounded object, and the forward stroke is complete, gives rise to the return stroke. Now, now we have seen how the lightning develops in combination of step leader for the forward stroke and return stroke. The typical electrical characteristics are summarized below. The forward stroke is 1 kiloampere to 2 kiloamperes, very small current, very slow to develop. Therefore, it is not visible to the naked eye. This is not visible to the naked eye. Very important. Then we have seen that return stroke has got huge currents. We have seen the reason for that. The huge current develops in conducting channel of the forward stroke. Forward stroke itself is invisible. The extremely rapid development return stroke. The minimum current in the return stroke is about 5 kiloamperes. It can go up to 200 kiloamperes. And then the rise time, the time in which the current reaches the peak, is typically 5 microseconds to 15 microseconds. Some rare cases, it can happen as rapid as 2 microseconds. It can take sometimes 30 to 60 microseconds or even more up to that time. So rise time typically is 5 microseconds to 15 microseconds. And the channel core temperature on the average is around 30,000 degrees Kelvin. Strictly speaking, is around 15,000 to 60,000, but on the average, typically around 30,000 degrees Kelvin. The velocity of the return stroke is very high because the already existing short circuit is there. The velocity is limited only by the inductance and capacitance of the things. That means surge impedance of the whole lot. It is half the velocity of light, extremely bright. And because of the acoustic effect, the channel extremely rapid, expanding rapidly, creates the acoustic effect, which we call the thunder. Now, once this current comes to near zero, it develops again what we call second return stroke, third return stroke. There will be several strokes. So in any average lightning, there can be several strokes on the always. Now, the other important point to remember is that cloud bottom is negative. That means lightning transfers negative current to the ground. And then what happens? The positive charge accumulated in the top region of the cloud that goes up to the lower ionosphere by means of a upper atmospheric event, the transient luminescent events. There's the blue jets, sprites, elves, tendrils, etc. They take the positive current up to the lower ionosphere. So now you see that the leakage of the charge from the lower ionosphere to Earth, the average being around huge current being discharged. Now this is made up by this lightning, which feeds the charge in the opposite direction because of this electrification, which has come because of the solar energy. So solar energy itself is the cause of lightning, fundamentally speaking. Now, on the overall, the summary of the basic characteristics are cloud potentials can be very small, and there will be obviously no lightning will be there. Cloud potentials can be right up to 100 million volts, even slightly more sometimes. The charge in a cloud can be very, very small, to 300 coulombs. The lightning flash, you see I have used a new word here, lightning flash. Lightning stroke is one, forward stroke plus return stroke. But in a total flash, the total number of strokes can be as many as 40. Typically, 4 to 5 strokes are there per flash. And then the peak current reduces from the first stroke to the subsequent strokes. For example, if you think of the first stroke to be 200 kiloamperes, considering the highest value, the second stroke can be typically 50, 60, or 100 kiloamperes. Third stroke can be 20, 30. Fourth stroke can be few, and then fifth stroke may not be there at all, like this. Now, currents in the lightning discharges to ground, typically up to 200 kiloamperes for negative strokes. Occasionally, very occasionally, there are positive strokes, which is difficult to explain. There has not been a single satisfactory theory, even for negative lightning, which is most common. So positive lightning, even less theories are there, but positive lightnings do occur. They are very small in percentage, maybe around 20%. The currents can go up to 360 kiloamperes. The currents can be larger, longer duration, and then all over the world, about 70 to 80% of the strokes are negative. About 20% of the strokes are only positive. The rate of rise of current in the lightning is of the order of 10 to the power of 11 amperes per second, which means 100 kiloamperes per microsecond. The number of strokes per second all over the world is anywhere from 2,000 to 5,000 strokes all over the world per second. So you'll see that lightning is a very huge phenomena involving huge areas in the atmosphere, involving huge currents, huge potentials. Everything is huge. Another important parameter for us to remember is that everything is probabilistic here. Everything is probabilistic here. That is shown here in some detail. Now, as I rightly here, some additional important features. NE is the probable lightning flash density. That means the number of lightning flashes per unit area. That means per square kilometer. It varies strongly with the latitude from the equator to the Arctic or Antarctic. The lightning flash density goes on varying. An expression theoretical, rather, I should say empirical relationship. I lost the word for a little time. Empirical relationship is that the number of discharges per square kilometer per year is 0.1 plus 0.35 sine lambda. Lambda is the latitude multiplied by 0.4 plus minus 0.2. Please remember this plus minus, very important. So it can go from 0.2, that's 0.4 minus 0.2 to 0.6, 0.2 to 0.6. So the variation can be 1 to 3 in a given region. In a given region, the minimum to maximum can be 1 to 3. So supposing you do something and you say lightning have reduced here by so much percentage in 2 years, it can be very false. It can be very, very false. You can get a realistic picture only if you observe for a reasonably long time. Let me say around 10 years, at least 5 years. 10 years would be better because the variation is 1 to 3, 0.2 to 0.6. Now, this point I'm making it here very clear is some people in India, they have said that by a very simple means, which I'll be discussing a little later, very, very simple means, they have reduced the lightning incidence and lightning fatalities. But how much percentage? No idea. Do they have an idea of what was the frequency of lightning in that area over the last several years? No idea. So it's a very, very hollow claim. It's not substantiated by real life. The reality is that it is the lightning incidence rate. How many lightning flashes per square kilometer per year is a highly statistical parameter. So it's very difficult to get a true picture unless it is studied over a fairly long period, something like 5 to 10 years. Now then we have got another important parameter called the isochironic level, or the number of thunderstorm days per unit area per year, or the per number of lightning strokes, number of days in a year in which lightning is seen. Number of days in the year in which lightning is seen. This is known as the isochironic level. The number of strokes per unit area, let us say, is Ng. Number of strokes per unit area is Ng. That's related to isochironic level by this empirical relationship. Please remember, these are all empirical relationship obtained by observation of the phenomena over many years, probably 20, 30 years. There's a statistical variation associated with it. So Ng, the ground flash density, that means the number of lightnings per unit area per year is 0.04 multiplied by Td. Td is the isochronic level defined above to the power of 1.25. So if you take, for example, Bengaluru, for most areas in India, the isochronic level is about 30 to 40. If you take 40 as an example, 40 to the power of 1.25 becomes approximately 50 to 60. So that multiplied by 0.04 becomes something like 3 to 4. So what you get is per square kilometer, according to this relationship, it is 3 to 4 lightning flashes can occur to the ground in 1 year, 3 to 4. But again, if you see this statistical variation, it can be 1 to 6. So if it happens to be nil in 1 year also, we need not be surprised. In fact, I am told that in England, there are some areas where there has been no lightning at all for last 10, 15 years. Some very isolated areas, they are very, very, very rare, very, very rare. I don't know if anything happened last year or not, but on the whole, they have not seen lightning over a very large period of maybe 10, 15 years. Now, here are some lightning photographs to illustrate what we have been discussing. You see, this is InterCloud Lightning. You see, this is one cloud, another cloud. The lightning discharge takes place like this. Again, between this cloud and these clouds, several interclouds, bridging several clouds which are all adjacent to each other. Of course, this is a cloud to ground stroke. This is again number of intercloud lightnings here within. This is an intra-cloud lightning. It's happening within the cloud. Cloud lightning happening within the clouds, the intra-cloud lightning. This is again a cloud to ground lightning. It has hit a tall object, a tree. You can see that very clearly. Very bright channel. These are the branches of the steps. Branches of the steps. So this is the main return stroke channel. and this has with a tall tree. I've shown several pictures only to show the difference between various strokes. You see, it's almost a straight line, almost. It has hit a building here, tall building, and then you have got highly branched here. There are some cases where a branch has gone several tens of kilometers like this horizontally, come back and almost hit the same area like this also. I couldn't get a photograph in the quick short time, but I think we have had a fairly detailed discussion on the various atmospheric events, lightning, transient luminescent events, and then intercloud lightning, intra-cloud lightning, cloud-to-ground lightning, characters of the forward stroke, return stroke, and then the distribution of the lightning strokes on the Earth, the statistical variations, things like that. With this, I would like to thank you for the attention, but it is now open to questions. That means which is open to the chairman, Mr. Gopakumar.
Thank you very much. Very
Can
nice.
Can I have a few minutes break? Just a few minutes?
Yeah, not an issue. Please. So, participants, we were listening for almost 1 hour 15 minutes to Dr. Nagabhushana. We had a detailed introduction or detailed information about the basics of lightning. Now we will go through the question answers. Of course, there are a few hands raised. We can see Mr. Yogendra Sharma, plus there were some questions on chat box. We will answer all those questions. Please bear with us for some time.
You want water? If it drinks water, the sneezes will come.
Nagabhushana sir is having some light throat, and he will have some water and join us very soon. Please bear with us. Sir, once when you are ready, you have to unmute yourself and start, sir. I have made mute.
Okay.
Yeah. So, sir, we have a question in the chat box. Participants, if you have any questions, please type on the chat box so that we can see your questions and answer. Now, sir, we have a question from Mr. Saumya Deep Chowdhury. I want to know how the charge separation occurs in the cloud, like how the negative charge accumulates at the bottom of the cloud and positive charge on the top. Sir, can you hear me?
Sir, he'll be back in a moment. Please give time.
Okay. Not an issue. We'll wait.
Yeah.
So parallelly, ladies and gentlemen, please note that the information, the video of this program will be available in our website probably tomorrow. You can see on our website, I'm just showing the website. This is VIDYUTSURAKSHIT.com. The program details are available. A lot of information are there. The electrical safety informations are there. Plus lightning protection information are there. And what interesting probably maybe to find out, you see here, there is a blog. On the blog, we have a lot of interesting subjects, lightning safety and education in India, plus some subjects related to the electrical safety. On the blog, if you search lightning protection, then you will get more information. Also, lightning protection in India and the cycle tire LPS, a lot of technical informations are there. As I said, we are trying to make technical information blogs on various subjects in this website. If you follow the website, you will be able to find out a lot of information. Now let's wait for some time. Once when Dr. joins, we will take up further.
Okay. I understand that there was a question which asked, how does the charge separation takes place? Now, as I mentioned to you several times during the lecture, there have been many theories which have been put forward. One of them I'll just mention. Suppose there is a water drop, large water drop coming down. Now, because of the ambient atmospheric field, electric field of the atmosphere, the top of the drop will be negatively charged. Sorry, the lower ionosphere is positive, therefore the top of the drop will be negatively charged, and then the bottom will be positively charged. Now, supposing there's a smaller droplet which is coming from below in the updraft, collides with this drop, it kicks out the positive charge, and then the negative charge remains. And because it's a larger drop carrying now a net negative charge that goes on coming down. So the negative charge starts accumulating below because all the drops ultimately have to come down by gravity. Gravitational force will be stronger than the force due to the updraft. That was one theory, but again, due to after a thorough analysis, theoretical analysis, was found that this cannot account for more than about 2%. Now, similarly, there were many other theories. All of them are incomplete even today. All of them are incomplete even today. I must really apologize saying that I don't have any theory for that, but this is the phenomena. But there are several theories like that. I hope I have only this much to offer.
Yeah. Thank you very much, sir. We have a few participants, those who wanted to ask questions. First is Mr. Yogendra Sharma. Mr. Yogendra Sharma, you can unmute yourself and speak to Dr. Nagabhushana.
Thank you very much. Myself, YK Sharma, Superintendent Engineer, GEP, Gujarat, from Colorado. I have seen number of fatal accidents, and I am really worried about that. I want to ask, whenever this lightning strikes comes, lot of fatal accidents are arised. But in spite of these new innovations to restrict the fatal accidents, we are unable to do it. When we will meet for a zero accident by use of advanced technology? This is my question.
Mr. Sharma, actually, your voice was a little bit echoing. I don't know whether the professor understood the question.
No, I could not. I understand. Can you repeat it?
I am audible now?
Yeah, you're audible, but the only thing is that the voice was echoing a little bit.
Now it's okay?
Yeah, probably.
Okay, thank you very much for giving me the opportunity. I am YK Sharma from MGBCL, Madhya Gujarat Beach Company Limited, and I had seen in my tenure a lot of accidents, not only from this electrical network, but from the thundering. But my question is that how we will restrict the fatal accidents, whatever occurred from the thundering? What precautions we have to take care of? Thank you.
How do we restrict? I think, sir, the question is how do we restrict from the accidents due to thundering? That is the question, right? Yeah.
Mr. Gopakumar, can you repeat the question to me?
Sir, how do we restrict accidents from thunderstorms or from lightning?
That's the most important aspect of this series of lectures. There are several measures. It will be very difficult to answer that in even in an hour. But on the whole, I'll just give it as a simple clue today, is that one must avoid outdoor activities. Particularly, for example, playing in the large fields. Taking shelter under the tree, being in the proximity of the tree must be avoided at all costs. In our rural regions, in particularly in India, agriculturists are then the people who are going on even two-wheelers. they tend to take shelter under trees when the rain starts. That's a very, very dangerous thing. Very, very dangerous thing. In fact, it is known that 50 to 60% of the fatalities due to lightning occur due to contact or proximity to tall objects like poles, trees, etc. That must be totally avoided. And then contact with horizontal fences on the ground, water pipes on the ground during thunderstorm weather. One important point, a simple point, is that between the first thunder, which is probably due to the intra-cloud lightning within the cloud, that's only a sound for us on the ground people. Between that and the first cloud-to-ground lightning, typically there'll be 20 to 30 minutes time gap. This must be made use of, and the persons must get indoors. When indoors, they must not touch the walls or any electrical gadgets, things like that. In a summary, this is all we can say today. But as we go further, we'll discuss this particular point in great detail in the next two webinars.
Thank you, sir. Thank you very much, sir. Yeah, thank you for the answer, sir. We have Mr. Narendra Daya. You can unmute yourself and speak, Mr. Narendra.
Yeah, sure. Hello, can you listen to me?
Yes.
Okay. My question is that when there are marine vessels in the sea, the potential differences may be very less. So whether the ships are at a low risk than the aircraft? That is my question.
Okay, it's a very good question. You'll see that if you see the lightning map at any time in the world,
yeah,
the lightning flash density is higher in the coastal regions.
Okay.
And on the seas in the middle region, the lightning flash density is lower. The reason is moisture is present, but dust particle presence is very relatively low. Because of that, in the middle region of the high seas, lightning flash density is lower, but coastal density is very high because moisture is very high. From the land, there can be dust particles, it will be very high. The tropical regions, desert areas, it can be very high. For example, middle of Africa, India, Malaysia, like that, tropical countries, it can be very high. I don't know whether I have answered your question fully. If I am not, please ask again. No, I have no problem.
Sir, the question was in case of in sea, the potential is almost the same, and how this is occurring. Anyway, I think we will be discussing about the protection part probably in the next, not probably in the next upcoming seminars. Please join us this coming week, Sunday and the week after. Four Sundays we are making this class, so we can further discuss. Now we have 4 more hands raised. Shrikant sir, you can ask the question.
Sir, my question is these moving objects on the earth, even though earth is moving, the trains, buses and ships, what my previous question he asked, no, the ship is located near to the port as well as inside the sea. So like the train is moving. So if it is like that, what is the effect on that?
You see, velocity of all objects on earth, like trains, buses, etc., is very small compared to the velocity of the lightning stroke. The forward stroke has got a velocity of the order of half the velocity of light, approximately 10⁶ meters per second. Whereas the velocity of this will be hardly 100 kilometers per hour at the most. So the velocity has got really practically nothing to influence the stroke incidence. Does it answer your question?
Yes, sir. Yes, sir. But the lightning strikes on the train. Nowadays, we are seeing the ships.
Yes.
Yeah, it is what basis exactly that and all. We could not get the.
As I told you, lightning flash density is typically higher in the coastal regions. If there is a ship in the coastal region, the incidence of lightning can be higher. But if it is the high seas, maybe 100, 200 kilometers away from the coast, the lightning incidence will be low. It will not be zero, but it will be lower. That's all. Nothing more, nothing less than that. But if it is near the coastal regions, incidence will be higher. Now, the step potentials will not be there in the same way as in the case of the earth-bound objects, because there will be no tall trees. But there can be a tall mast which attracts the lightning. That's what happens invariably. To attracts the tall mast. If there is anybody close to the mast, then there can be a shock due to the proximity or contact also. Now, this proximity or contact with a tall object will be discussing in detail with some amount of elementary mathematical explanations also in our next webinar.
Yeah. Sir, actually, I have seen the fishes near the surface also, it is dying, sir.
Oh, okay. It happens because the current has to flow. You see.
No, though it is equally potential, the water is the equipotential. How the fishes are dying? The question is the equipotential on the sea surface.
No.
Fishes are dying.
Yeah, you have answered your own question. See, the water has got a finite resistivity. It's not zero. It's a very important thing. Water has got a finite resistivity. So when the current flows through the water, per unit meter, there will be some amount of voltage drop. The fish body is also having a finite resistance only. So part of this current will flow through the fish body and the fish will die.
Okay, sir. Thank you very much, sir.
Same way, when the person stands proximity of a tree, same thing happens. Finite resistivity of the soil drives current through the human body.
Thank you very much, sir.
Yeah.
Thank you, sir.
Very
Thanks
interesting
for the question.
Very good question.
Yes, sir, Mr. Sri Ashok Kumar, you can unmute yourself, and if you have a question, you can ask. Also, Engineer Smruti Ranjan plus Mr. Rupam, your hands are up now. You can unmute yourself and you can ask the question if you wish. Also, Mr.
Yes, sir. Yes, sir. I have a basic question. Sir, myself, Smruti Ranjan, I have a basic question.
Please, we can hear you.
Sir, Earth is regarded as a electrically neutral object, and same amount of negative charge and same amount of positive charge. So how can it be taken as a negative charge for body?
Which one? Please, question is not very clear to me. Can you kindly repeat it once again?
Sir, you take Earth as a negative charge particle for global capacitor. The Earth is taken as a negative charge particle, but Earth is neutral, same amount of negative charge and same amount of positive charge. So why it is being considered as a negative charge particle?
It's a very interesting question. The Earth as a whole is an electrically neutral body. There's no doubt about it. But the surface has got a negative charge because of the global capacitor, because of the charge on the ionosphere. It induces a negative charge on the surface. There will be equal positive charge inside. So the total neutrality will be there, but the surface charge will be negative. Does it answer your question fully or not?
Okay, sir. Sir, again another question regarding formation of charges, static charges in the cloud. We have earlier taught that when it is due to the frictional energy, when the moisture along with aerosol it moves upward due to heat, it accumulates energy due to frictional energy and it accumulates charges in the cloud. Is it a theory, sir?
Yeah, that is one of the theories that have been put up earlier. As I told you, Simpson's drop theory, Geisel's theory, and this frictional theory. There have been more than 10 theories, but none of them are enough to adequately explain the full phenomena. The friction also gives rise to these charges. What you say is right, but that phenomena is not adequate to explain the full phenomena. That's the point.
Okay, thank you, sir. Thank you.
Thank you, Mr. Welcome. We have Mr. Rupam. Please, you can ask the question. Please go ahead. We can hear you. Hello.
Yes, please.
Hello.
Yes, please.
We can hear you.
Myself Rupam. Good afternoon, sir. Myself Rupam Datta from Power Grid Corporation, Mizoram, sir, Aizawl substation. Sir, actually, in Aizawl and in Northeast India, we face a lot of lightning-based fittings of our lines. Actually, I have gone through some of the articles on lightning. and I studied it independently as well. Sir, can you throw some light on this is the meaning of this continuous current components of lightning, sir? And what are the M components of
Can you kindly repeat it? It is not clear to me.
Sir, actually, we know that in lightning there are so many phases involved in multiple strokes lightning, sir. So
Yeah.
I have gone through a lot of articles regarding this lightning phenomenon.
Yeah, very good, very good.
Sir, I have gone through some one term called continuous current, sir. Continuous
Okay.
current.
Yeah.
And what is actually I have learned that from some of the articles that this continuous current is the main component of lightning that causes the damage because of its periodicity. A long period of current flows, sir. Can you throw
It's a very, very good question. Very, very good question indeed. So I told you a little while ago that lightning has got multiple strokes, right up to 40 strokes within one lightning flash. What we see can be called a lightning flash, within which there will, on the average, 4 to 5 flashes, strokes will be there, and then 40 to 50 flashes can occur in one flash in the extreme level. Of course, minimum is 0. That's not a big thing. Between strokes, there will be a current flowing through. It will not go to 0. So initially what will happen, the first current, for example, highest is 200 kiloamperes. It will be followed by a current of something like 5 kiloamperes for about a millisecond. It will be followed again by about very small current, say something like 200 amperes for about a second. Then there can be a second stroke. Like this, in fact, if you see the standards for testing of aircraft, the full wave shape consists of 4 components, A, B, C, D. A is a 200 kiloamperes peak, front time approximately 10 to 15 microseconds, tail time approximately 75 microseconds. I will talk about these details later in another webinar. And it will be this first stroke of 200 kA will be followed by a 5 kiloamperes in the standards, a flat current wave lasting 5 milliseconds, followed by again a current of 200 amperes for a full second, and then followed by 1 second stroke of 100 kA, 200 kA, followed by 5 kA for 5 milliseconds, followed by 200 amperes for a second, and then 100 kA as the second stroke. So different conditions have attracted different standard definitions for the current wave. Now this shows essentially that between strokes, there will be small currents flowing for a long duration. The overall energy in these low current long durations will be much higher than the total energy in the big strokes. What you say is perfectly right. I hope I have explained this to you to some extent.
Sir, one more doubt I have, sir.
Yeah, yes, please.
What are the M components of lightning, sir? Is there any term called M components, sir? And what about the JK processes of lightning, sir? What are JK processes of lightning?
I think they're I should say, they're too very detailed. I think I will not be planning to going through that. They are not very relevant to our particular theme. I have not studied them in detail, so I will not be able to answer your question. I am very sorry. I hope you don't mind. What you say is right. J component, K component, yes, they are there, but they are very different from the point of view of human hazards or hazards to equipment, buildings, etc. They are not very relevant. That much is certain.
The last question, sir. Sir, during this step leader propagation, sir, we have discussed that it was some bidirectional leader was helping the step leader to get propagated from the atmosphere to ground, sir. During at any instance, say suppose a lightning, the step leader has reached a location at some altitude, and then there is a bidirectional leader. So, which polarity of the bidirectional leader will get attached to the lightning, sir, for a negative lightning?
The negative end will come down towards the earth. The negative, the positive end, we will go towards the end of the cloud domain, and then when the field becomes too small, it extinguishes. Whereas the negative end propagates towards the earth. The cloud has got negative charge that feeds it. The cloud doesn't have too much of positive charge in the bottom zone. It cannot feed positive charges. So positive side extinguishes. Negative charge, the negative charge can be fed to any extent, up to 100 coulombs, 300 coulombs. So that starts developing. So the positive end extinguishes, the negative end develops towards the earth. I hope I have answered the question.
Okay, thank you, sir.
If it's not clear, if not clear, please do ask again. No problem.
Thank you very much for the questions. Now we will take a few questions from the chat box. Mr. Amritlal is asking, volcano tips are susceptible to lightning. It looks like a statement, or I don't know whether it's a question. Do you wanted to add any answer, sir? Volcano tips are susceptible. Are they susceptible to lightning or something like that?
Yeah, see, if they are tall enough and if there is a cloud formation on top of that, because of very high temperatures on tip of the volcano, there can be ionization very easily. Thermal ionization can take place in addition to the electrical ionization. So that can attract. But volcanoes are so rare. The studies have not been there in a very detailed way. I hope.
Sir, the next question is from Mr. Praveen Kumar Sinha. Can you explain or show any example of calculation of NE, the lightning flash density, lambda of location of TD, thunderstorm days? So some information about lightning flash density and number of thunderstorm days.
I gave in the last two slides, I have given the expressions for the lightning flash density as a function of latitude, as a function of the area. Both I have given already. I don't know if they need anything more than that. I don't know about it.
I think it is already there, Mr.
It's already
there. What you can do is in the National Building Code, in the Part 8, Section 2, in the National Building Code, the India's the map and the number of thunderstorm days informations are included. Probably we can also give you the detail. You can send a message or you can send your email address. We will also put it on the answer to you, or we can also include it in our blog. You can download it probably after 3-4 days. So thank you very much for the question. Now, Mr. Randir Kumar, why sometimes lightning stroke hits low level irrespective of high level available?
Can you kindly repeat it?
Why lightning strike hits low level objects irrespective of high level available nearby?
Why does it hit the lower object than a higher object? Essentially, that's what it asks.
Yes.
You see, I believe that there will be a separation between the two. The leaders must be able to reach up to that level completely. If the electrical strength at the tip of the leader becomes high, it will not propagate. On the other hand, if there is a lower object having a weaker strength in the electric field intensity, rather local electric field strength of the air in that vicinity, that will develop further. That will happen, but this will be relatively rare. It's not very rare, because as I told you, there will be branched leaders. Sometimes the branch goes and develops and forms a complete stroke, and the main leader does not propagate further. The simple reason is that the electric field breakdown strength of air can vary very strongly from point to point in the microscopic range. That's the reason for this to happen.
Yeah, thank you, sir. There is also one Mr. Randir Kumar has added. We have 220 kV tower which has low level than nearby 400 kV tower. Some day ago, lightning hit 220 kV tower and not the 400 kV tower.
Yeah, there is the same answer as before. There are 2-3 things. Where is the step leader coming towards? Is it coming towards the taller one or the shorter one? The separation between them, how much is it? Is it several hundred meters? It can be 700 meters easily. If there is 700 meters difference, the probability is definitely towards the taller object. There is no doubt about it. But as I told you, if the electric field strength of the air is weaker in the proximity of the smaller, rather less tall objects, shorter objects, it will develop towards that more efficiently. That's the same answer as before earlier question.
Mr. Shailesh Kumar is asking to repeat this lightning return stroke.
Complete return stroke?
Yes. I would request Mr. Shailesh, we will upload the video probably today evening. You can look at the video, and since the return stroke is already explained by Professor, you can look at the video and understand it. I hope that will do the job.
I can certainly go back, but if it's essential, I can do that. No problem for me.
Yeah, sir. I think anyway, we have 3 more sessions. We have further.
Yeah, that is true. That is very true.
Then Mr. Vikas is asking whether it is possible to predict a lightning strike occurring possibilities in raining by observing nature of rain, or we have to wait till rain to be stopped completely. So the question is basically whether it is possible to predict lightning strike occurring possibilities. Shall I answer this question,
Yeah,
sir?
yeah. You please go ahead.
Yes, Mr. Vikas, yes, the lightning, the possibilities of lightning stroke are nowadays measurable. There are field mills or the meters available which can tell you the electrostatic charge. And once when the charge during thunderstorm, before thunderstorm, the charge starts building up. And once when the charge is more than certain level, of course, lightning is going to happen. And this is a sign of probability of lightning. And these the commercial the products are available. You can predict in fact in advance. Not with the rainfall, the pattern of rainfall, it will be very difficult to claim or find out.
You're right. You're right. Mere rainfall. There are rains without any lightning also. There are very heavy rains without any lightning. So directly rain and lightning is not directly related, but the two are what if they together in a relatively weak sense. But dry weather lightning is also seen without lightning. Sorry, without rain, lightning is seen. So rain is not essential, nor is lightning essential in rain. Both of them.
Yes. So, sir, another question. If high mast is from Mr. Ajit Navani, if high mast is 30 meter with lightning arrestor is available, but nearby vicinity lower height building safe near the tower. So, Mr. Ajit, it's already as Professor explained. Can you rephrase that? Even though there is a tall object nearby, lightning is hitting the smaller objects.
Yeah, I explained that twice already. I don't mind doing it again. See, the step lead is coming down in steps. Why does it come down in steps? At the tip of the leader, the charge density is low. That must be fed by the parent cloud. There will be huge charge available that develops. Once it develops in that finite time, the electric field strength of the air in the surrounding direction, in the surrounding air, would have different values in different directions. It will develop in that direction in which the electric field strength of the air is lower. So that can be different. It can be different. It can be towards the shorter object. So that can happen towards shorter object. There's no doubt about that part. Does it answer the question or not?
Yes, sir. Yes, sir. Yeah. Now we have two raised hands. Mr. Ashok Kumar, you can unmute yourself and you can speak. Or if you have no questions, Mr. Soumyadeep Chowdhury, you can speak again. You can unmute yourself and ask the question. You are also raising your hand.
Good afternoon, sir. I am Soumyadeep from Voltage Department in IISc.
High Voltage Department? Which department?
In IISc, sir. High Voltage.
High Voltage Department? With whom are you studying?
Sir, I am working with Dr. Uday Kumar.
Very nice. He will have the answer better than me. Anyway, what's your question?
Sir, my question is that you told in the beginning that from the negative charge in the bottom of the cloud, the bidirectional leader starts propagating.
Yes.
Sir, I want to know why means the leader propagates in two directions, not in only towards the ground. Why it starts in the upward direction also?
Very good. I will tell you this. I'll repeat this. See, in the bottom, we have got a negative charge region of the cloud. Below that bottom, we have got a positive charge region. Now, these are all broad regions. They are not short. They spread for kilometers, as wide as the cloud itself. Wherever there's a negative charge, it induces a positive charge below that. So when there's a local breakdown, when the sufficient electric field density develops, there'll be a local spark. Now, that develops in both the directions. No doubt about it. Both the directions. Because there is positive charge available here, negative charge available here in both the directions. So it develops in both the directions. But development finally will be towards the earth because the cloud can supply any amount of negative charge. It has got a huge cache of negative charges. Whereas positive charge, where does it come from? So it has to terminate somewhere. There is no abundance of positive charge available anywhere, whereas negative charge on the contrary available in huge quantities. So that develops. The other part does not develop. Okay. It's a very good question. It's a very good question.
Thank you, sir.
Welcome. Welcome.
Thank you. Thank you. Thanks to all of you. Sir, I think we have answered almost all the questions. Now there is no question. Also in the chat box, there is no question. Now there is Shivaram. Why generally lightning hits coconut trees when there are some other trees available at height? This is
There's no such preference at all. Taller tree, and wherever the streamers develop, that's the attractive point. That's the attractive point. That's all. Wherever there's an attraction and wherever there's a suitable electric fields.
Yeah. Hello, sir. Your voice is not coming now. Okay. Hello, ladies and gentlemen. So we have. I don't know what happened to Naga Bhushana sir's voice. Probably it's off, or probably he has been maybe disconnected because of the internet connections or something like that. Now back to the program. We had a good participation. About 120 people participated in this program. So thanks to all the participants. The purpose of the program, as I said, it is to increase, or it is to create awareness about lightning and the lightning safety measures to people. We have put on the chat box, you can see a feedback form. So we request you to fill up the feedback form so that we can improve if necessary. I will post it again in the chat box. So request you to fill up the form and give the feedback to us. Now, the next session, part 2 of this session is in the coming week. Part 2 session, we will be talking about details of the hazard due to lightning and the basics of protection of humans. So another interesting subject. It is on 29th May, the coming Sunday, 11 o'clock. Here we will talk about the fire hazards due to lightning, electric shock hazard to humans and animals when they are in contact with the tall pole structures, or the role of inductance of current path, the effect of rate of rise of stroke current, step potential, role of soil resistivity, typical soil resistivities of concrete blocks, shocks due to contact with the objects carrying lightning current, activities proven to be lightning stroke, and type of injuries and fatalities, plus the protective measures for humans. This is the subject which will be discussed on the coming week, 29th May, 11 o'clock. So we request you to join on the coming week, 11 o'clock. For the time being, thank you very much. Thanks to all of you for joining the program. See you in the coming week. Thanks and bye-bye.